Hey everybody, and welcome back to Algebra 2 Online. So today we're going to talk about how to solve exponential equations, but ones that don't need logarithms to solve them. And in the next video, we'll do ones where you do need logarithms to solve them. So some of them are like this one here, and these are kind of like the nicer version, because every once in a while you'll get something where, like in this problem, you have a base 2 exponential on the left, and you can actually write 32 as 2 to the 5th, right? So you can say 2 to the 2x equals 2 to the 5th. And you basically don't need logarithms at all, because the only way 2 to something here can equal 2 to something else is if those things on top, the 2x and the 5, are equal to each other. So 2x has to equal 5, and then you could just divide by 2, and you get 5 halves. So this is kind of like, I always view these problems as sort of like factoring versus quadratic formula. So there's a lot of times you just need the quadratic formula. That's kind of like the harder version, and that'll be ones where you like need a logarithm to solve them. But then there's some where you can just kind of look at it and rewrite maybe part of it as the same base as the other side of the equation, and then you can just kind of drop the base like I did and just work with the exponent and then solve it out from there. So I also wanted to talk about, so last time we saw that number e, and there is actually a logarithm that goes with e, which shouldn't be super surprising because every exponential has inverse log function. So if I draw this kind of picture, right? With a picture like this, if you have like some exponential function e to the x doing that, then the inverse, which would sort of take you back to where you start, is this thing called the natural log. And I will actually show you it in class, like on your calculator. There's a button for it, but we abbreviate it literally just like ln and then of x, like that. And you'll see this on the homework, really from this point on in the unit. It's just a special log. It is log base e. So you could also write it this way, with the base e like that, but you don't really ever see that. Really, the story goes just that this one pops up so often in math, just because this exponential pops up so often. So we just sort of were lazy, and we didn't want to write log base e every time, and so we just sort of gave it this notation. But it doesn't mean anything super fancy. It's just literally log base e. And kind of next time, you'll see some problems where if you have an exponential function like this one over here, if you wanted to cancel that e, okay, you can just take the natural log of both sides, like that, and then because they're inverses, natural log of e to the 2x, you cancel the natural log in the e part, and you just get 2x on the left, and then natural log of 7 is just some kind of weird decimal. It's just a weird number. And so you could just divide natural log of 7 by 2, and that would be the answer to that thing. But these are the ones that we'll kind of do next time. But I just wanted to introduce it here because there are a few things on the homework with them that you'll see. And I figured if we're also talking about these kind of weird logs, we should talk about another log that gets a special name, and that is something called the common log. So this is the one that is inverse to 10 to the x. So if you have 10 to the x, and it's kind of taken like x to y there, you can kind of draw this sort of curve in, and the thing that takes you back from y back to x is this thing common log, and literally we write it like this. It looks like we just forgot to write the base, but we didn't. It just isn't there. So it is the same as writing the base 10 in there, but just like with the natural log or log base e thing up here, how we don't write that, we often you just won't see this, 10. This one is common because really our number system is a base 10 system, and so there's a lot of times where you get 10 to the x, which is really big in things like orders of magnitude, a lot of like scientific notation stuff. There's just a lot of things where powers of 10 show up, so it's kind of common, and so they just called it the common log. And so you'll see it used when we solve equations like this one. Here if this is kind of jumping ahead again, this isn't exactly what your homework's on, but if I was trying to solve this one out, I could add 7 over, I could divide by -1, I get that. And then really at this point, you would just have to do like common log of both sides. You would just take log of both sides, and then this would cancel. So you would cancel the log and the 10 there. You would get just x and then this thing. So that's kind of how we will use these in equations, but all the ones on the homework, all the exponential equations for the homework for tonight is basically just nice ones where you don't even need to bring in logs to solve it. You can just kind of do it intuitively, just doing tricks like we did. Over here, where we wrote 32 as 2 to the 5th. So I just want to go through just like a few more quick examples, ones that are kind of a little harder than that first example, but all examples where you don't need logs to solve it. So all of these things you can just solve using tricks where you kind of rewrite the base the same on both sides, and then basically ignore the base and just work with the exponent, okay? So in this one, if you've got a base of 1/6 and a base of 36, probably not too hard to see that we can get these to both be 6 to something, right? So we could write 1/6 as 6 to the -1, and we could write 36 as 6 squared. Then I can just kind of keep all this stuff here. And at this point, you just have to do a little bit of simplifying, basically. So when you do a power of a power, you multiply, right? So we would have 6 to the 3x plus 2, and then we would have 6 to the 2x plus 2 there. And this is the point where I literally would just ignore the bases, right? The only way you're going to have 6 to something equals 6 to something else is if those things in the exponent are equal, right? So you really can just drop them and just say, okay, 3x plus 2 has to be 2x plus 2, and then you could just like minus 2x, and you can cancel those 2's. So, oops, sorry, can't do math. So if you minus 2x, you get just x, and equals 0. The nice thing about exponential equations too is, there's no like exponentials are defined everywhere. So whatever I get should work. You don't need to worry about things like we did with even roots, where sometimes we were getting answers that just didn't really work, and it was just a product of the fact that the even roots weren't defined everywhere. But these things are really well defined, so whatever we get, you should be able to plug it in, and it should work. You shouldn't need to like throw out answers for exponential equations like this. All right, so this one looks even scarier, probably, and really you're just trying to find what number to use as the base on both sides that could be the same, right? So you're always sort of bringing the number, making them smaller, right? You're not gonna, like if you've got a base 2 over here, right, and a base 4 over here, there's no way that you're gonna make the base 2 into a base 4. You can't go up, so you can only go down. So what we'd have to do is turn all this stuff into like the lowest base that we see, which would be 2 is the lowest one we see, right? So if we start doing that, 4 is 2 squared, right? And then, actually, we can even do something better. Look at it a second time. There's actually a 2 we could take out of both sides, right here, and we could divide this by 2. So we could actually work with smaller numbers a little bit if we just divided by 2. Oops. Divided by 2 on both sides. Definitely not like necessary. You don't have to do that, but it's good to work with smaller numbers rather than big ones. So that's really the same thing, just divided by 2. So now I'm going to do what I was saying. So 4 is 2 squared. And then over here, I want this to be a 2 to something, right? I don't want a 1/2. So I would do 2 to the negative 1, which is 1/2. And then I have 2x minus 7, just kind of left over. Still not good enough because this constant in front is not a base 2, right? But you actually can make it a base 2. If you go through like your powers of 2, you would see that this thing actually reduces to 2 to the 10th. And so now I'm going to multiply those right there. I'll also distribute that negative 1 there. So I have 2 to the minus 2x plus 7. Now this is going to be good because everything can be combined into base 2. So here, the property when you multiply with the same base is that you add these. So I would add those together, and I would get 2 to the minus 2x plus 17. And now I can do the thing where I just sort of drop the 2's, right? I can just ignore them. Jump up here, I can just say that 2x has to equal minus 2x plus 17. So then I can add that over and divide by 4. And that's it. So that's probably about as hard as they really can get. Really just always try to think about it as taking whatever you have and reducing it down to the smallest base you see, right? So try to, in this one, you're never going to be able to make something like a base 2 over here equal a base 4. So you basically have to make any of your other bases, bring them down to base 2. That's the idea.